In this video, I'm going to show you two examples as to how to use Newton's method to be able to approximate the solutions to the zeros of functions. So let's say we have a function f of x equals x squared minus 2x minus 48, and we're given the initial guess that x sub naught is going to be equal to 7. Now, this is a pretty silly problem to use Newton's method on. And the reason being is because, well, we could just factor this. This could factor into x minus 8, x plus 6, and equals 0. And that would yield the solutions x is 8 and negative 6. All right, so there's no real reason for us to use Newton's method on this particular problem. But because we know the solutions, well, let's see what Newton's method does. All right, so now recall that Newton's method says that xn plus 1 is going to be equal to x sub n minus f at x sub n divided by f prime x sub n. And for us, we're given that x naught is equal to 7. All right, so let's just set up the first of these iterations. All right, and I'm going to set it up both generally as well as with 7. So first thing we need to do is we need to take the derivative of this function, and the derivative is about as easy as we can get, right? The derivative for this is going to be 2x minus 2. All right, and all I'm doing is I'm just taking the derivative of that function. And now let's just set up the general formula. All right, so what I'm going to do is I'm going to set up this formula first by just substituting xn back in wherever I see an x. All right, so for this problem, only, x sub n plus 1 is going to be equal to x sub n minus, now we're going to have the function, and remember our function was x squared minus 2x minus 48, so that's going to be x sub n squared minus 2x sub n minus 48, and then we're going to divide that by the derivative. And we're just going to use 2x sub n minus 2. So this is the general setup for this particular problem. Now, let's find x1. And x1 is going to be equal to x naught minus x sub 0 square minus 2x sub 0 minus 48 divided by 2x sub 0 minus 2. Or if we know what x sub 0 is, remember x sub 0 is 7 up here, then x1 is going to be equal to 7 minus 7 squared minus 2 times 7 minus 48 divided by 2 times 7 minus 2. And if we wanted to, we could just throw this right into our calculator and get an approximation. So I'm going to show you, first of all, the long way to do it, and then I'm going to show you an easier way to do this in the calculator. All right, so just by substitution in our calculator, we're going to say 7 minus the quantity of 7 squared minus 2 times 7 minus 48. And then we're going to divide that by the quantity of 2 times 7 minus 2. All right, and this is what x1 is. x1 is 8.08333, etc. Now be careful with MyMathLab. It's probably going to ask you to approximate to a specific accuracy. So we have 8.08333. All right, now the problem is, think about the next step. Okay, so x sub 2 would be equal to 8.08333 minus 8.08333 squared minus 2 times 8.08333 minus 48 divided by 2 times 8.08333 minus 2. This is painful to type into the calculator. All right. Let me show you an easier way to perhaps do this in the calculator. Now, you are going to have to type it in once, okay, the formula. But the way that I'm going to show you means that all you have to do is type it in once, and then the calculator is going to do the rest of the work. So first thing you're going to do is you're just going to type in whatever x naught is. In this case, it's 7, and you're going to hit enter. Right now, the number 7 is stored in answer. All right, so if I hit enter, 7 is stored in answer. And to get answer, you just hit second and minus. All right, so right now, 7 is an answer. That's great. So we can use Newton's formula And instead of typing in, and you might remember, I'm going to go back a few steps. Remember we had this animal that we typed in? Couldn't I just replace 7 with ants in each of these steps? So I could just go back, and I'm not going to do it here. And you might remember that when we typed this in and hit enter, we got 8.08333. You're probably sick of hearing me saying that. Now let's use ants. So I'm going to say second ants minus the quantity. So I'm just replacing all the 7s here with ants. So that's going to be second ants squared minus 2 ants minus 48 divided by 2 ants, right? So this is 2 times 7, or 2 times ants minus 2. And then I'm going to hit enter. Hey, oh, I see. I didn't do that right because 8.08333 is stored in the ants. All right, so let me do it one more time. I'm going to hit 7, and I'm just going to bring up what I just did. All right, so now it's the same thing. I just should have hit 7 and then enter. All right, and now we get 8.08333. That's great. Now, if I hit enter again, notice that 8.08333 is now stored in ants. And so what that means is we just found x2. So x2 is 8.00049. Which is a lot easier to work with. Should the answer be 8? Because remember at the very beginning of the problem, didn't we solve this analytically? And we just factored it and we got 8. So doesn't it make sense that our answer should be getting closer or converging towards 8? Now, we can do this a couple more times. So let's hit enter again. And now we get 8.00000. I think it's 7 zeros. 1, 2, 3, 4, 5, 6, 7, and 1, 7. All right, so that's x3. And I know the problem didn't ask for x3. All right. If we wanted x4, we could just go to our calculator and hit enter one more time. And notice what happens is we get 8. That means that the calculator has basically exceeded the precision, or I'm sorry, the problem has exceeded the precision of the calculator. So it just has to surrender and say that, okay, as close as I can get is 8. It's not 8 exactly. It's probably like 8 point, a whole bunch of zeros, and then like a 4 or 5 or something like that. But this is a really easy way for you guys to just go ahead and plug in the solutions. All right. So let me take a look at another problem with you all as to how to use Newton's method to be able to approximate the solutions. All right. And by the way, the only two things, and x4, according to our calculator, is 8. All right. But remember the original problem, it just wanted x1 and x2. All right. And we found that. Okay. So this is a value for x1, and this is a value for x2. So we're good. All right. Now, another problem. This one, we definitely should be using Newton's method to solve because we can't solve this analytically. So we're going to write the formula for Newton's method. Okay, so we'll do that first. Then we'll use the initial approximation to, again, approximate x1 and x2. All right, so we got to find the derivative, just like we did before. So let's start with that. Our derivative is going to use a chain rule, so be careful. So f prime at x is going to be, the derivative of negative x is -1. So technically, it's -4e to the minus x minus 7. If we remember Newton's method, all right, and I'm going to write it up just because it's the first time we've seen it, xn plus 1 is equal to x sub n minus fx sub n divided by f prime x sub n. If we use Newton's method, then what we can do is we can just use the original function, use the derivative, and just substitute x sub n wherever we see an x. All right, so the setup for this problem is going to be x sub n plus 1 is equal to x sub n minus the original function, which is 4e to the minus x sub n, minus 7x sub n. So all I'm doing is I'm just replacing these x's right here with x sub n. And it skipped all the way up for some reason. Right. And then the denominator is just going to be the derivative, which is -4e to the minus x sub n minus 7. let's now find x naught, and we're going to use the calculator to help us. Okay, so now x naught, the very first one, I'm just going to set this up. It's going to be ln of 2 minus 4e to the minus ln 2 minus 7 ln of 2 divided by negative 4e to the minus ln of 2 minus 7. All right, so let's go into our calculator and let's use that trick that I showed you. So I'm going to clear this out. I'm just going to type in ln of 2, and I'm going to hit enter. All right, now ln of 2 is now stored in ants. Okay, so now all I have to do is just type in this formula, except I'm going to use ants wherever I see ln of 2. All right, so we're going to say second ants minus quantity. Now remember, it was 4e to the minus ants. Okay, so we're not using ln of 2, we're using ants. Minus 7 ants. And then we're going to divide that by negative 4e to the negative ants. And then we're going to say minus 7. Times 7 minus 7. All right, and our answer we get is 0.37625. All right, so, and I'll show you how, after we're done with this, to make sure that that makes any sense whatsoever. All right, because we get these answers, and how do we know it makes any sense? So 0.37625 is x1. All right, now we'll hold on to this, but we need x2. All right, and all we have to do now is just hit enter. So I'm just going to hit enter, and we get 0.38774. All right, so this is 0.38774, and we're done with this problem, but I'm just going to take it a step further and illustrate that you can get x3, x4, and how we know that we're getting on the right track, and then how we can check it. So let's just get x3 and x4. I have a feeling that they're going to get really close to one another really soon. So I'm just going to hit enter again, and I get 0.38758, so 0.38776. All right, so 38776. And then let's just hit enter one more time in our calculator, and we actually get the exact same answer. Okay, so notice that this answer is the exact same thing, and that's how we know we're getting to really close to the correct answer. All right, by using Newton's method. So this is 0.38776. Now, how do we know that this answer makes any sense whatsoever? Well, couldn't we graph it and look at the zero of the function? All right, so let's graph it, and let's see if the intercept is anywhere close to 0.38776. All right, so I'm going to go into y equals. Remember, our function was 4e to the minus x minus 7x. Okay, now I'm going to graph this function. I'm going to zoom standard. All right, and let's zoom in just a little bit. So I'm going to zoom in a couple times, actually. So I'm going to zoom in there, and I'm going to zoom in again. All right, I'm going to move over just a little bit here. By the way, for those of you that are looking at where the x is, notice that x is really close. Okay, 0.38563. I'm going to zoom in just a couple more times. This is how you guys can check your solutions. And I'm going to zoom in again. All right, and then I'm going to zoom in just one more time. It's kind of painful to do this. And I'm going to move over on the axis. So we get 0.38772. If I was to round it, what did we get? 0.38776. So in fact, Newton's method seems to be even more precise than the calculator by sitting there and zooming in continuously. All right. In fact, it probably took us just as long to be able to use the calculator method. All right. So hopefully this illustrates the power of Newton's method and also how to go about utilizing it. In the next video, what I'm going to do is I'm just going to do one more sort of problem with respect to Newton's method. And it's not going to be a function. Next time it's going to be an equation. So I can show you how to solve equations utilizing Newton's method.